All right. Welcome to this presentation on which I have given the title Reconstructing the Direction of a Neutrino Using Neural Networks. And I think this might not say a lot to you, so I have also given it the alternative title, The Art of Giving Eyes to a Computer. So I wanted to keep you, this in the back of your mind until further in the presentation. So I want to begin by discussing what we are made of. So if you were to ask a bakery, for example, they would say that a yummy cake, it's made out of eggs and flour and sugar, and these are like the constituents of this yummy cake. But if you were to ask a chemist, for example, they would say that the people, the earth, everything around us is made out of helium, of oxygen, of carbon, iron, and gold, out of the periodic elements in the periodic table. So this is kind of a map of all the things that are around us. This is from a chemist's perspective then. But if you ask a physicist, they would say that the entire universe is just made out of electrons, for example, which is electricity. You would have photons, which is light. You would have something called quarks, and this is all described by something called the standard model, which is also like a map of all the things around us and in the universe. So what I want to focus on is, you can see in this standard model, which is all the particles, you see three very weird particles here, which have Greek letters and look kind of strange. And these are called neutrinos. And this is my area of interest. So now you might be wondering, what is a neutrino? Well, a neutrino, it's a very small particle. It weighs almost nothing. It's very light. And there are also plenty of them in the universe. So if you were to look at your thumb or at your thumbnail right now, about 100 billion neutrinos flow through your thumbnail every second for your entire life. But you don't notice them because they, A, are very small, B, they weigh almost nothing, and the most important thing is they rarely interact. So they never collide with things almost, and you don't notice them, and you can't feel them, for example, but they are everywhere. So why should we then care about neutrinos? Why should you care about neutrinos, for example? Well, if a star explodes out in the universe or two black holes collide with each other, it will emit some particles. And these particles could be heavy nuclei, for example. You would have neutrinos, and you would also have some light because you can, for example, see the explosion or see the collision. But the thing is that heavy nuclei and light, they would collide with things in space. So collide with interstellar gases, intergalactic gases, for example. But this will not happen to neutrinos. They will just propagate through the universe uninterrupted. So because they don't collide with things, almost never. So if we find out where the neutrinos come from by some method, we could get an insight in the most extreme and mysterious events in the universe. As I said, for example, black holes, we want to know more about them because they are very, very interesting. This could also give us very valuable astronomical and cosmological information about the formation of the universe and stuff like that, popular science things. So how could we see neutrinos? Well, I mentioned that they were very hard to see. So let's say that we have a source of neutrinos. It would spit out some neutrinos, for example, a black hole or a star exploding in the universe. Neutrinos would flow out and some of them would go towards the Earth. So what you do then is that let's look at the Earth and let's turn it around and let's zoom into the south part. And here you have Antarctica. Okay, so let's go to Antarctica and let's build this observatory. Let's build this station, this detector. This is not to scale, so you can see this is the entirety of Antarctica, but this station is just a few meters across. So what this is that we have 1, 2, 3, 4 of these antennas. So these are exactly like the antennas on the top of your house, for example, or the antennas inside your phone, which you can communicate with Wi-Fi or 4G, for example, or the antennas on a radio. So these are just radio antennas listening for radio signals. And then there's also this fifth antenna down here. So these are dug into the ground. So what happens then when a neutrino comes into the South Pole? to Antarctica? Well, let's describe it in 4 steps. So the first step here is that the neutrino comes into this giant block of ice, which is, Antarctica, because it consists of a few kilometers thick sheets of ice. What happens then is in step 2 is that the neutrino might interact. I said this was very rare, but sometimes it happens that the neutrino collides with the ice inside of the South Pole. And this will create some positive particles and it will create some negative particles. And in step 3, what happens is that these positive particles and negative particles separate. And this separation will create radio waves. So some radio waves will be emitted inside the ice. And on step 4, the radio waves will reach our antenna station and we can listen to them. We can look for them, we can measure them, just like you can measure radio waves on a radio. So what do the radio signals look like? Well, I have an example here. So remember again, we had 1, 2, 3, 4 antennas here, and we had a 5th antenna. So in total 5 antennas. And this is an example of 1, 2, 3, 4, 5 antenna traces. And the 4 first ones look almost the same, and the 5th one is a bit different. That's the antenna right here. So it basically looks like some sort of signal. So this is a neutrino interacting inside the ice, and we can see the neutrino. But I don't know about you, looking at this signal traces, I can't really tell you where the neutrino come from. Did it come from just above, to the left, or to the right? I'm not quite sure. Maybe you know, but I didn't know. I wanted to know where does the neutrino come from, because we want to know where are these black holes, where are these stars colliding. So what we do is, I need to tell you something about neural networks. Okay, so you might have heard about it. Some other common terms being thrown around are artificial intelligence or machine learning. So what this is, it's a very old method, but it has quite new applications. So for example, self-driving cars use neural networks for driving, and people are also able to diagnose cancer, and also during this pandemic, diagnosing COVID-19 using neural networks very successfully. And also there's examples of facial recognition. There's tons of other applications, but there's some of them. So a neural network, what is it? Well, it's something that mimics the biological brain. So it makes these connections between neurons, and it basically just tries to mimic the brain that we have inside of us, because our brain is pretty smart. So let's just build something that almost looks like our brain. And you need to train a network just like you train a person. We go to school, you teach children, this is blue, this is red. You have to teach the brain something. So how do you train a network? Well, it's quite simple, actually. The first step is that you give the network some example data. So for example, for self-driving cars, you would show the network some images or videos of people driving cars. And for diagnosing cancer, you would show the network some images of cancerous cells, and then show it some images of healthy cells, and it would learn from those. So the second step is letting the network do some predictions on new data that it has never seen before. And the third step would be to punish the network if it's wrong. So basically by punishing, I mean changing the numbers inside the networks, turning some cogs and pulling some levers, changing the structure of the network, depending on how well it performs. And the fourth step is just repeating 1, 2, 3. The network is then learning. So example, if you have set up a new phone for the past couple of years, if you used something like Face ID, you have shown it your face, and the network inside your phone has learned from example data, which is images of your face. So you have probably used the neural network in the past. So now, how do we actually figure out the neutrino direction? So we take simulated data. We can simulate data of antenna traces and directions, and we would plug it into the computer. And the computer has this neural network, and it will plug in the example data, the simulated data inside the neural network. And this is where the title of the talk is, the art of giving eyes to a computer. So this is, we're kind of letting the computer see data and learn from it. So now that we have new data coming in from the South Pole, let's say that we build these stations at the South Pole and we have new data coming in. we would plug this data into the computer, and the computer now remembers the neural network. It has learned from previous examples, and it can now spit out the direction of the neutrino for us. That's very nice. And that was the main goal that we wanted. We wanted to know where the neutrino comes from. Okay, so conclusions. Neural networks, they work wonderfully for the problem at hand, and especially considering that classical methods have not worked as well as this. And there's also a lot of large potential for this method to improve. So some opportunities for improvement are, you can use larger models, for example, you can have more and better training data, and there's other ways to improve. And it could, however, be quite difficult to see and understand what the network is learning and what it's seeing and which patterns it's looking for, but this can be visualized, and I refer you to report for that. Let's see. So how did it actually go, just quickly? Well, let's say that you're on the South Pole, you're this penguin, and you want to figure out where the neutrino came from. Just randomly guessing would give you that the neutrino came somewhere inside this circle of 360 degrees. But using the neural network that I developed, you can get the direction of the neutrino to within an accuracy of 4 degrees. So you pretty much can point in space, okay, this is where the neutrino is coming from. All right, that's it for me. You can find more details on my website if you want to go there. And also, if there's time for questions, you are free to ask.